switch, we just stop sharing and then share the next one, right?
Well, it's not a matter of stopping sharing, but just stop viewing this PDF. It's just sharing the whole screen, not the application.
All right, maybe you can help me do the switches.
Okay.
Good morning, everyone, and welcome to day 2 of the LISA Symposium. We are going to have 4 plenary talks in the morning session, beginning with Valeriya Korol.
Hello, can you hear me well? Yes. Okay, so good morning to everyone. It is my pleasure to present you with updates from the LISA science team. And let me start by showing you the faces. The faces of the LISA science team. The team has been selected in 2024 after the LISA adoption. And since then, it has been fully established, including this last 3 new additions. So this includes Katja Grimani and Zoltan Heinemann, who are our complementary scientists. So these are experts that covering science which is not directly explicitly mentioned amongst LISA science objectives. Katja is an expert in space weather, and Zoltan is a multi-messenger expert. And also Jonathan Kerr joined us recently after he has been elected as a consortium representative since the consortium reset. So why does the LST exist? The LST monitors the correct implementation of the science objectives of the mission and maximizes its science return. The LST acts as the focus for the interest of the scientific community in LISA, and that's the direct quote for the LISA Science Management Plan. And what it means that practically we support ESA and NASA in maximizing LISA science objectives, advise on science performance, calibration, data products, and eventually archives. We define how LISA science reaches the community through alerts, catalogs, early release science, and we work by establishing working groups, and we'll prepare the framework for the science topical panels that I will introduce later. And all of this is defined in this document, the LISA Science Management Plan that you can find online. It's public, and many of the things that I say comes directly from here. So if you're curious about the mission programmatics on the science side, that's the correct place to look. And the LST positions in between the project on the left side, so you have ESA, NASA, and the ground segment. And here on the left, the LST and the science community, including the consortium. And as you can see here, we represent a direct bridge between the science community and the project. And we bridge you with the project through the working groups and the science topical panels. The LST is selected after the mission adoption, and it will remain in place throughout the mission until the end of the post-operation phase. It is chaired by ESA project scientists and co-chaired by the NASA project scientists. It includes 17 scientific members that are selected through an open call coordinated between ESA and NASA. And it can include up to 2 complementary scientists that are also selected via an open call by ESA. And it also includes a consortium representative elected by the consortium. And the people on the LISA science team are appointed for 3 years and may be renewed. So this is the current composition of this first LST after the adoption. And just to be extra clear, let me outline the differences between the consortium and the LST. So consortium is an independent scientific body supporting the LISA mission. It focuses on community-driven preparation for using and interpreting LISA data. as well as community building and promotion of LISA and LISA science. While the LST is appointed by ESA and NASA, it is a formal link between ESA, NASA, and you, the scientific community, and it advises on science-related mission questions, the project, and we work in the working groups, and via this working group we can involve you as well, you, the community. At the moment, we have 6 active working groups. This is communication, figure of merit, outer list, L3 catalogs, science topical panels, and alerts. And I will go through each of these groups, highlighting the objective, the status, and deliverables. So I will start with the catalog working group. It is chaired by Astrid Lamberts and Nikos Karnezis. It has many internal but also many external experts that you can see here. And the main objective of the group is to define the requirements and the content for the final LISA data product, this L3 catalog. And this diagram hasn't been shown yet, so let me quickly walk you through this. So basically, we start, the LISA data starts at level 0, coming from the satellite, right? We go to level 1 via time delay interferometry, then to level 2 via global fit, and this final step is the catalog, right? It's the final data product that we will release. And as a matter of a couple of weeks ago, the working group has delivered the first version of the catalog definition document, and Astrid Lamberts will tell you everything about it later in the session. So this document will be public to you and available on the ESA website soon. So then I can switch on to the alerts working group that is chaired by Zoltan Heinemann and myself. We are currently consisting of internal members only. We are the youngest working group within the LST, but we will be soon inviting external experts based on specific expertise and requirements that we are outlining at the moment, so stay tuned for that. And our objective is to define the strategy for the alerts, so the trigger, code, cadence, content, updates, as well as retractions. We provide input to the science ground segment on low latency pipeline requirements. And we, very importantly, we also aim to engage with electromagnetic and multi-messenger communities to make sure that the follow-up will happen timely. And as a matter of a couple of weeks as well, we have delivered the first alerts document that provides an input on the science ground segment requirements for the low latency alert pipelines. And because Astrid will tell you everything about catalogs, I wanted just to outline the overall philosophy of our alert memo. And basically, the philosophy is that of maximum release with minimum latency, and that because we identify the risk of losing an electromagnetic counterpart to a LISA source as a measure risk for the achieving LISA mission science objectives. So we recommend issuing alerts for all sources that pass some predefined significance threshold. And this is some statistics that will be chosen by the low latency pipelines when they will mature with time. For instance, it can be a false alarm probability. And so this means that we recommend issuing alerts not only for massive black hole binaries that are iconic LISA transient sources, but also for MRIs and IMRIs that may be rare and may also have electromagnetic counterparts that we want to follow up, as well as stellar mass black hole binaries for multi-messenger science, burst, unmodeled signals, and maybe even some special cases of galactic binaries. And specifically, in our view, the alert should not require any precise localization before informing the community. We recommend to get the alert as soon as possible and then let observers to find the best strategy to follow up. We also recommend to include all relevant parameters returned by low latency analysis, such that you have all the information you need to independently assess the follow-up visibility and the risk. And of course, these parameters should come in easily digestible format for observers, and the alert should be in a citable format like astronomy telegram, for example. Then we talk a lot about updating alerts. You will see those details in a document directly when it will be public. And basically, the idea is, of course, we update the alerts as the source and parameter estimation improve. And that includes also after the merger, when we get better and better understanding of the noise. And of course, all the threshold and numbers that we give in this document are just an indication and should be revisited when the pipelines and the rates will become better understood. And finally, let me highlight that this is, of course, the LST recommendation, but implementation feasibility of the LISA alert will be decided by ESA and NASA and the Science Ground segment. But if you feel strongly about it and you want to communicate to the project your ideas, please talk to any of us on the LST about the alerts. Let me then switch to the Figure of Merit working group chaired by Antoine Petitot and Alberto Cesana. The group consists of both internal and external experts that are worked on figures of merit as part of the consortium project, and Chiara yesterday already gave you some examples and the definition of the figures of merit, but if you missed her talk, let me remind you that figures of merit are metrics that connects instrument performance to the mission science objective. And they allow us to assess how technical, operational design changes could affect LISA science return. So Chiara gave some excellent examples yesterday. And the objective of this group is to define a concise set of figures of merit and to deliver and maintain a tool that performance and operation team can use independently. So as of now, we have reviewed the figures of merit tool that has been developed as part of the consortium, and this is the logo of the consortium tool. We have streamlined and updated some metrics, simplifying here and there, and basically arrived into an LST-endorsed set of figures of merit, and we are working on implementation and maintenance strategy for this tool. Now let me switch to the Science Topical Panel Working Group chaired by Elena Maria Rossi and Stephen Taylor. Currently, it comprises only internal members. And science topical panels are the expert groups that will be called by this science management plan. They will be focused on selected science topics during the early release science time. So this is the first 12 months of the data collection following in-orbit commissioning. And the goal of the science topical panels will be to interpret the early LISA data and to produce science papers. And each team will work on one specific theme. So the objectives of this working group is to define the role and the remit of the STPs, recommend topics, team composition, expertise, responsibilities, develop procedures and timelines for the topical panels, define their interactions with the collaboration, consortium, and the community, and develop the associated publication policy for the STP papers. And at the moment, the group drafted procedures for forming science topical panels. It has been discussed within the full LISA science team, and so they are in the process of implementing the feedback and in producing a document outlining the procedures for selecting STPs and their composition. And the group will be gathering input from the science community as well, and the process for this, for gathering the feedback is also something that they are working on at the moment. Another group is the outer list working group chaired by Neil Cornish and Jonathan Gare. And this group's main objective is to define the LISA collaboration outer list. So the LISA collaboration outer list is again something that is called on in the science management plan, and it is the science management plan defined this list as consisting of two lists. The heritage list that recognizes a significant contribution to the mission that has no expiry, and then a member list that covers people who are actively contributing to science operation with a 2-year roll-off period. So people actively working on LISA while during the data acquisition and releases. And so the objective here is to define transparent criteria for inclusion in both lists and establish procedures for nomination, selection, and maintenance of these lists. And the group has reviewed different practices in different missions and instruments, developed some initial descriptions for these two lists, and is currently drafting the membership criteria and selection procedures. And last but not least is the communication working group, which actually ties all of these working groups together. It is chaired by Anna Heffernan and Kristalin Smith. And the objective of this group is to coordinate clear and consistent message, but also progress tracking across the LST. We also maintain the links with the consortium and ESA and NASA communication team, and we act as an outward-facing group between the LST and the scientific community. We share updates and provide routes for communications, questions, feedback, engagement, and so on. No, so we have established an LST email box that you see here. So if you want to reach out, please be welcome. We are developing content for the ESA LST website that will be also mirrored by NASA and the consortium website, as well as preparing the FAQ, LST-related FAQs. And we give regular community updates at meeting, conferences, and any venues. So with this, I will leave you with the summary slide on the work across all the working groups, and I'm happy to take your questions.
Thank you, Valeriya. Questions?
Hello, thanks for the talk. One of the things I'm interested in knowing is what are some of the examples of figure of merits that you define, especially in terms of astrophysics and detection, part of the science?
Yeah, so basically each of the LISA science objective outlined in the LISA Red Book has some associated figures of merit. So Chiara, for instance, yesterday presented a figure of merit on the standard sirens, for instance, in the terms of detection numbers, right, but also some specific on the parameters that are required. So that's one example, and basically each of the science objective would have some calculation that checks whether it is whether the science objective is satisfied or not, and each figure of merit has an associated traffic light. So when the performance and operation team runs the tool, right, if they hit the red light, that's not good for science, right? If it's green, of course, any changes that they have within the instruments are not affecting science. So this is the philosophy of this instrument. And actually, there will be a paper coming very soon on the figure of merit tool developed by consortium through the years leading to now.
Hi, I have a rather specific question about the alerts, but I don't mind asking because you're co-chairing that group. When we first started thinking about having this separate alerts pipeline, I think we were focusing mostly on short duration transients, and the list of things that would classify as alerts now is much broader than that, including long-lasting signals that pass some threshold. And I can imagine, depending on where those thresholds get set, that the alert pipeline ends up looking like a mini global fit, and the alerts end up looking like mini data releases, which is maybe fine, but is that the intent? Or how are these thresholds going to be set to keep these pipelines from getting very blurred together?
So I think that the pipeline question is more your expertise, but from the scientist's point of view, we believe that it's really important to not lose any chance of any electromagnetic counterparts. And for instance, thinking about MRIs and MRIs as well, right? This is maybe one of the least understood LISA sources from theory perspective, because we know so little about smaller black holes that we believe that it would be of a great addition not to have alerts for these sources as well, and to give astronomers the chance to look for the follow-up so that we can understand them better and know them better. Yeah, and I guess the same applies for other sources, but it's true, the pipelines then, yeah, will need to have some different architecture to include this, or maybe there are ways that you can streamline alerts from the global feed or something like that.
There's an online question. Does the communications group also address public outreach, or who is responsible?
Yeah, that's a good question. I think that at the moment, because we are the first and LISA science team, right, we were mainly focused in internal communication as well as establishing bridges with the consortium and the community, but it's true as the time goes and we approach LISA launch, outreach will become an important part of communications, and I don't know this for sure, but I envisage that a future LST may well deal with the public outreach as well.
All right, let's thank Valeriya again. Okay, Ryan and Peter, if you could help me out here. Okay, so go ahead. So I'm going to give you a 5-minute warning at 20 minutes.
Okay.
And then I'll stand up and look irritated if you go too long.
Yeah. You're going to wave?
Are we still sharing here?
I think we stopped.
Okay.
some noise. Like that? Seems good.
All right, next we are going to have Ryan DeRosa, who's going to tell us about the optical metrology system.
Okay, good morning. I'm here to give you an update on the LMS. So I'm going to cover 5 subsystems. So 2 of these are in development at NASA, which is where I'm coming from. But the other 3 development teams that I'm going to address, they were very collegial and they made me slides so that together we can give you a pretty comprehensive update of the system as a whole. So what's in the OMS? So this is a graphic that you can steal from the Red Book that shows you one of the links in a LISA constellation, right? So this is like half of a spacecraft on either side of a long arm, and the 5 blue and white text boxes are calling out the subsystems that I'm going to go through the status of today. So if you start on the left, you've got the laser, which is the little green box in the diagram. It feeds its light down onto an optical bench, which isn't shown per se in the diagram, but that's where all these little mirrors and beam splitters are living. Now, a little bit of the light on that bench goes and probes the position of its associated test mass, but the vast majority of the light ends up getting sent towards the middle of the diagram where you've got the telescope. Telescope launches it across the long arm, where it gets picked up by another telescope, brought down onto the far bench, gets routed to one of these little blue circles, which is a quadrant photoreceiver, or QPR. That's where the laser field gets turned into an electronic current, goes down a cable into the purple box, which is the phase measurement system, or the PMS. And so those 5 ones are the ones we're going to go through today. And the point of all this hardware is to track the separation either of a proof mass with respect to its local spacecraft, or indeed of the distance between the spacecrafts themselves, because that's how we combine all the information to actually find out the proof mass to proof mass separation. And this all has to be done at the picometer level. Now, unfortunately, we don't start in the OMS with picometers. We have to get through 7 or 8 orders of magnitude of frequency noise first, 3 to 4 orders of magnitude of clock noise, and 1 or 2 orders of magnitude of tilt to length. That's all done in post-processing, okay? That's in the computer, but that's not to say that the OMS hardware here is just sort of sitting down in the picometers waiting for that post-processing to happen. It's also got a family of functions and performance requirements that actually enable this post-processing to succeed in the first place, and we'll go through many of those. And if you want to imagine what the sort of raw signal that the OMS is dealing with in the long arm, it's a heterodyne interferometer, so there's laser fringes, they're flying by 10 million hertz. The arm length is drifting tens of thousands of kilometers a year. We're constantly getting pushed around by a few millimeters worth of frequency noise, and the OMS is tracking, okay? It's tracking the phase of the laser all the time with picometer precision and with only a few picometers of extra noise added into the signal in that narrow, millihertz to 1 hertz signal band. All right, so that's what we're doing. If you want to think about it in phase terms for the wavelength laser, it's like few microradians kind of phase tracking. So now we'll go through all the subsystems. We start with the laser. First and foremost, laser has to deliver 2 watts of power, and it can't just be any power, it has to be stabilized power. And it has to be stable at low frequency and at high frequency. So here, when I say low frequency, I mean the signal band, right, 0.1 millihertz to 1 hertz. And for the laser, some of its requirements, when we say high frequency, we mean not even just the maximum heterodyne frequency the signal might get, but it's got requirements up to twice the maximum heterodyne frequency, plus a little margin. That could be up to 60 megahertz. And so when we talk, or you see posters about people doing experimental verification of the laser requirements, they have to deal with 12 decades of Fourier frequency that they're measuring over, okay? It's no joke. Now, the power has to be stable at low frequency to limit the radiation pressure noise on the proof mass. This is not actually an OMS noise budget term. That's team femtoG, we're team picometer. But at high frequency, it does have to be stable to conserve the purity of the phase readout. Now, the frequency of the laser itself has to be stabilized as well. So I told you on the last slide that we do 8 orders of magnitude suppression of the frequency noise in post-processing, but that's only good enough if you start from a low enough level. So the frequency is actively stabilized in the laser. And it's got 3 modulations that it has to apply to the beam in order for this post-processing to work. So there's a few gigahertz sideband modulated onto the main beam. That's how we transmit the information of the different clocks around the constellation. And then around 1 megahertz, there's another modulation. It's a pseudo-random noise stream. And that's how we range the spacecraft against each other, because we do need to have some understanding of their absolute separation in order for the time delay interferometry to succeed, right? So this is done to sort of meter level accuracies. And then it turns out that on top of that ranging modulation, there's a further modulation which we actually use to communicate data from one spacecraft to another, because only one of them may be in contact with the Earth at any given time. And all of these modulation requirements, they have to be there to allow the post-processing to function, but they also have got their own amplitude stability and phase stability requirements attached to them, okay, to the application of the modulation itself. Now, another big challenge for the laser is it has to last for a long time, okay, like more than 10 years, not only in orbit, but also on the ground for testing. And this drives a lot of reliability and redundancy needs into the system. And anyone who's done experiments on the ground will understand that like keeping a stabilized laser working for 10 years that's not made to go into space, like that's not so easy, okay? And so this has to be done in orbit. So here's the architecture of the laser system. It's complete alphabet soup. I wouldn't worry too much about memorizing this. Maybe just look at one of these red boxes that says LH hot, all right? So that's a laser head. There's a hot and a cold, that's main and redundant, and so there's one pair of those associated with each of the optical payloads in the constellation. Now, if you go into a laser head, you'll find it's got an electronics module and an optics module, and if you go into the optics module, that's where you'll see, the quote laser, right? So it's a MOCBA architecture. It's got a master oscillator, main oscillator, MO, and a power amplifier. This is also where the phase modulator is, and so the MO and the PA, that's where the 2 watts comes from, all right? So to do the frequency stabilization, each of the spacecraft has got a reference cavity, that's the little green box at the bottom, and any of the 4 MOs that are in that spacecraft can be locked to that reference cavity and serve as the frequency reference lead for the whole constellation, right? So anyone that you need to can do it. Now for the power stabilization, this is not done actually in the laser head itself. There's a separate sensor that's installed on the optical bench. This is because since it's there to limit the radiation pressure noise on the proof mass, we try to measure the power fluctuations as close to the proof mass as possible. All right, so this is a free space detector on the bench that feeds the signal back to the laser. And unless you're on the bench where it's all free space, all of the power, laser power, is routed around in optical fiber. So this is also book kept as part of the laser system delivery. We're building these at Goddard. And when you count them all up, how many you need for flight or for spares, or for ground testing. There's more than 400 of these things that need to be assembled and characterized. So here's the status of these main pieces of the laser system. So at the Space Agency, they like to talk in this language of technology readiness level, or TRL, where TRL 5 means reasonably mature and TRL 6 means quite mature. And we would say that all of the main components of the laser are sitting at this level now. If you look at the next thing that we're going to be building, we also like to use this language of EDUs and ETUs, where an EDU is a development unit and an ETU is test units. That's really like a flight-like unit that you don't intend to fly. And so for the laser head, the electronics and optics modules, they're going next into their ETU phase. But for the stabilization hardware, for the frequency reference and the power reference, they're actually, the next thing we'll do is the flight models. And we're at this level of maturity because at this point, we've demonstrated all of these requirements for the laser system, either by test or analysis or test and analysis. And that's like a very brief statement to describe like an enormous volume of work over many years. So there's some pictures of the hardware here. On the bottom left, this is one of the reference cavities inside of its thermal shield. The 2 pictures in the middle are different evolutions of the main oscillator, so that's where the NPRO lives, if you like to think about these things. And then on the right, that's the optical module, so that's the main oscillator and the power amplifier getting put together. And the person there gives you kind of the idea of the size of these things. So the laser sends its light down a fiber into the optical bench, and the OB needs to route this laser beam to all the various interferometers. So there's there's a test mass interferometer on the bench itself. It has to send light to the associated bench in the same spacecraft. And then also most of the light ends up going to the telescope. So that's the path that I've tried to highlight here in the layout. And of course it starts with the fiber. That's this item here on the left where it says starting point. And it's got to match the 10 micron mode of that fiber into the 2 millimeter mode that the telescope is going to want to receive. And so in order to do that with a really nice wavefront and sort of nanoradian pointing stability, they have designed these cute little custom catalysis bonded lens assemblies. And I'll show you a picture of one in the next slide. The optical bench also has to be careful about controlling the polarization all over the bench, because that's how all the multiplexing is done. And it also has to control the stray light. And so there are apertures and baffles and beam dumps kind of littered all over the place. And as the beam is getting routed through all these different things, the thing we don't want to measure is the change in the dimension of the optical bench itself. And so they build the whole thing on a zero-dur base plate, and anywhere that they can, they catalysis bond the elements instead of using a glue or an epoxy. They also, on the OB, they cannot avoid actually transmitting through optics. And so they've got a very strict rationing of how much glass they're allowed to go through, because the phase will also feel changes in the index of refraction as the temperature walks around. This is the development status of the OB. So they had their design PDR successfully already, and they're getting ready to build 2 full-sized units. So one's an engineering model and one's a structural thermal model. Right now they're building the components for the engineering model. There's pictures of these here. So there's a clip on the bottom left. On the bottom right, these are these lens fiber injectors that I was talking about. And then in the middle, these are the little imaging systems. So there's also catalysis bonded, and there's one of these in front of every single quadrant photoreceiver on a bench. And in the top right, that's the base plate for the structural model at Talasiso after they have gone and lightweighted it. So they've machined out some of the material from the inside. Whenever you do that with zero-dur, you incur some subsurface damage in the glass. This compromises the strength of the glass. You get microfractures. And so after they would have taken this picture, they would have taken this whole base plate and just dipped it into a vat of acid to smooth out the cracks. This is nasty business if you've ever looked into doing it. So the EM is going to start building early next year, and then the STM is going to start building actually already this year. So all of these components will go on there, and will get populated into this kind of cityscape. So here's where I have to tell you that they sent me the CAD rendering of how this is going to look like, but my government training kicked in and told me I can't show that kind of detail to a room full of people, but now I understand it was actually shown yesterday already. So you did get to see how complicated it looks, but not from these slides. And in order to do this build, they've developed this fancy robotic alignment positioning and bonding technique. So after the light leaves the bench, most of it goes into the telescope, and it gets blown up, all right? So there's a very high magnification afocal telescope. Comes in at 2 millimeters, leaves at 300 millimeters. And the reason we need to do this is to maximize the amount of power we're getting across the long arm link. And as we're doing this, just like the optical bench, the thing we don't want to measure is the change in dimension of the telescope. And we end up solving this problem essentially in the same way as the optical bench. We put it into a very good thermal environment, and we make the whole thing out of zero-dur glass. And I'll show you a picture on the next slide. No, maybe 2 slides. Now, it's not a picture-taking telescope. I think people understand this. It's not like Hubble or Webb. Nevertheless, it still has to have a very good wavefront, 36 nanometers, for a variety of reasons. For the current design we have now, which is this 4-mirror design you see in the schematic, essentially this wavefront requirement drives a very tight positioning tolerance on that secondary mirror. So that's the small one all the way on the right on this slide. So then it goes across the long arm. In PowerPoint, you just flip your telescope around, and now it's a receiver. But now the beam is like 20 kilometers wide, okay, because the arm's pretty long. And we are only condensing that central 300 millimeters down into the 2 millimeter mode for the bench. So if you start with 2 watts, you get something like half a nanowatt on the other side, if you're lucky. It doesn't sound like very much, but it's enough. All of the path length stability requirements that we talk about on the transmitter, they apply the same to the receiver. Also, the wavefront of the receiver has to be very good. Somewhat interestingly, it has to be good for different reasons than it has to be good in the transmitter. There's also an additional feature of the receiving telescope, which is that it's attached to the spacecraft, and as the receiver spacecraft is jittering around in angle, the field elevation of the beam will change inside the telescope. So the rays take a little bit of a different path through all the surfaces, and that could have a different length, which we don't want to happen. So you have to suppress this effect, which we can do by controlling the design of the surfaces of the mirrors. So the status of the telescope is here. A few years ago, we made a few EDU telescopes and an STM with L3 Harris up in Rochester. This is a picture of the EDU. If you come for the tour tomorrow afternoon at Goddard, we can show you this exact thing. It's out on the table. And we did a lot of optical testing with these EDUs. Wavefront's excellent. We've also characterized the sensitivity of the wavefront to the environment. This is good. And with the SDM, we actually did path length stability testing, including at the picometer level. This also looks good. So right now, we're running an ETU contract, again with Harris. We had our SRR back in May, and this ETU is going to go into not only the first optical integration of a payload over in Europe, but it's also going to go into a reasonably sophisticated test campaign to make sure that not just the telescope, but the whole optical payload, we understand how it responds to changes in the environment. So ETU telescope contracts going full speed. At the same time, just at Goddard, we made 2 structural model telescopes. This is just metal, no glass. This is just for interface testing for where we actually bolt to the support structure. Those got finished in May, got shipped to Europe, and I think they were integrated onto the higher level test article last week. All right, once that 2 millimeter beam leaves the telescope, it comes back onto a different bench, and it gets routed to the quadrant photo receiver. So there's 4 on the A side of the bench. These are these gray boxes, one's got a red circle. And the QPR is made up of 3 pieces, okay? So there's the actual semiconductor itself, the quadrant photodiode. It's got front-end electronics behind it, and it's all inside of a housing. They've got their own set of challenges. So the QPD, it's got to have pretty low capacitance to control the coupling of the readout electronics noise. But it also has to have pretty low crosstalk in between the 4 quadrants because we're not just using it for precision determination of lengths, but also for precision orientation. The QPR in general has got to handle a pretty broad range of powers because we're going to ask it for useful signals before the constellation is fully aligned. And so it's going to be way down on the beam power. It has to work, and the same as it does when you've got as much power as it could possibly get. It's got to have its phase characterized very well, including against perturbations of the environment, including matching between the 4 channels coming out of any QPR. So we have to know exactly how it behaves all the way up to the maximum heterodyne frequency, 30 megahertz. And it has to have a very good alignment knowledge. This is basically rendered, levied on the housing. So this is not the position, you understand. It's not the longitudinal picometers. This is the lateral alignment. We need to know it sort of at the 10 micron level, and we also need to know that it's not going to move. So it has to be made to be very insensitive to drift with the environments. The development is also split up into many parts. So there's groups working on the QPD, group working on the electronics, the housing, and then also the testing. So this is a collaboration between several groups in the Netherlands, including Dutch industry. There's also a group in Belgium, and there's the AEI Hanover. It was explained to me exactly what each one of these groups is doing, but please don't quiz me because I can't believe I will reproduce it properly. And they're going through an EM campaign right now. They're using commercially sourced diodes for this just to have schedule relief. This is not their plan necessarily going forward. They're going through TVAC testing. They've sent me a picture of that here. And so you can see 3 QPRs under test, and they've been very heavily thermometrized, and they're all not sitting on the metal base plate, but instead they're stood off on little glass discs to better replicate what it would be like on an actual optical bench. This is supposed to go through the end of the summer, and then it'll feed into some further testing at Ganes. And we have to remember that they need 48 of these things in flight, in addition to all the ones they need for ground, and they all have to be tested and characterized, right? So it's a small thing by itself, the QPR, but it's still a big piece of work to deliver this. That's where the signal becomes electronic, and then it goes down a cable into the phase meter. Phase meter is also split up into parts, so there's a PCU and an IPU. You can hear more about this from Ada tomorrow. This is a rendering of the PCU, which has this very snazzy black and gold aesthetic. And this is where the readout actually happens, okay? So there's 3 types of interferometers that get fed into the PMS. There's the long arm interferometer. That's where we only have that half of a nanowatt, and so the shot noise is commensurately higher. That gets budgeted in the PMS noise. So in addition to that shot noise, all of the other readout noise that the PMS provides, it can only be 9 picometers per root hertz. You've got more light to deal with in the other interferometers, and so there you're talking about better than 2 picometers per root hertz. But it also has to deliver the alignment signals, right? So the PMS is figuring out the orientation of the spacecraft with respect to the beam coming across the long arm, and also the orientation of those test masses with respect to their local optical benches. This readout not only feeds the attitude control, but it also needs to be used in post-processing to subtract the tilt to length signal, right? Because this long arm interferometer wavefront sensing, that's the witness for the attitude jitter of the spacecraft themselves. It's also got a lot of functions that relate to the post-processing. So all of those modulations that I talked about with the laser, they come from the phase meter, all right? So the sidebands or the pseudo-random noise code, those are generated in a phase meter, sent to the laser where they get modulated, then they end up getting demodulated or decoded in a different phase meter. So there's a very complicated and critical phase meter laser system interface. And just as the laser system has to be careful about how those modulations are applied, there are phase stability and strict timing requirements on the generation and demodulation of these modulations inside the phase meter. This is how all the post-processing is set up to succeed. Additionally, one of the laser main oscillators in the constellation is serving as the frequency lead. All of the other ones are locked to it, and that frequency control signal comes from its associated phase meter. So here's the development. The PMS as a whole had its SRR last autumn, and right now for the IPU, they're in an engineering model phase. They're doing the design right now. That's supposed to go through the summer. Once this is complete, they'll go into assembly, integration, and test. And I don't have it on the slide because I didn't actually know exactly what it was, but I heard this morning that the PCU is in a similar state. All right, so to conclude, OMS is a huge effort. There's a huge number of parts. Some of these parts have huge numbers of details. Some of them you have to make 6 or 12 or more, and it all has to work together in the end. That being said, we know what we have to do, but we have to get doing it because launch is pretty soon. And that's it.
Thank you very much. Ryan, questions? So I can start with one, which is sort of a broad question. What worries you most about these many interlocking systems?
If we mistake the as-built static offset of the point-ahead angle, we will not close the constellation.
Okay, that would indeed be bad. Other questions?
There's an online question. It says, in which year will the telescope and laser be in their advanced FM construction so they will become sort of budget neutral?
I don't know. I have a manager for this.
I have a question.
Go ahead.
Yeah, so I only recently appreciated how small all of these parts are. And, you know, I'm an astronomer, and in astronomy, we used to be like the biggest telescope is the best, right? The biggest CCD is the best. So how come, for instance, even the photoreceivers are so tiny?
Yeah, so the photoreceiver side, well, this is a good question. So the photoreceiver size has to accommodate fully capturing the laser beam. We don't want to lose any of it. And then those little lens imaging systems that were on one of the slides, they've got a magnification of a few, and then the telescope's got a magnification of 135. And this all actually has to be matched. And so the size of the photodiode is related to the size of the telescope, and the biggest size of the telescope is related to how much we can afford on the spacecraft. Because we can't just make the primary mirror bigger and bigger. That makes the telescope, if you don't lengthen the telescope, that makes it fast. It's already about as fast as we can confidently make it, and the spacecraft doesn't get any bigger. And so there's a huge trade space that we've fallen onto a point design in, which literally links the size of that photodiode all the way up to the size of the spacecraft. And you could change any of these variables and play around with the noise curve, but everything else has to give. Yeah, it's interesting.
All right, let's thank Ryan again. Okay, our next presentation is going to be a remote one by Astrid Lamberts. Astrid, can you hear us?
Yes, I do. Can you hear me?
We can hear you indeed. Fire when ready.
And you're seeing the wrong screen. I'm assuming you see the presenter screen, right?
Yes, we do.
Okay, let's try this again. Up. Oh, come on. This one should work.
Yep, we see it.
Okay, great. Well, good morning or good afternoon, everyone. So I'm going to present this on behalf of the LISA Science Team Catalog Working Group that was chaired by myself and Nikos. I would really like to thank anyone who was involved in this, which is also a lot of people outside of the LST. Before I start, unfortunately, my neighbors have started drilling. And I know this is a remote presentation. It's not fun. I think only Nora would be able to make this pretty, but I'll do my best to make this as painless as possible. So our goal was really, and it's really a privilege to imagine what the LISA data could be. And that's what we started to do, essentially, knowing that the LISA data needs to be able to serve many different communities who will be searching for very, very different things. We also were convinced that the LISA data needs to be accessible for non-gravitational wave experts. There's 2,000 people in the consortium, give or take. I think we should be reaching much beyond that. And so that was the goal of this catalog definition document, is to have the first imagination of what the data could be. So Valeriya showed you a representation of the different data levels. We could have a slightly different view of this. It's basically the LISA data is a bunch of sources coming out of the spacecraft. Some people will actually just want to look at that level 0 or level 1 data, and because they know that they're looking for the, the big long orange shape, or they want to just look at the bulk of this. Most people will probably want a bit further analysis of this, which is done probably in the global fits, which will produce lists of candidate sources and posterior distributions for their parameters. And this will give us the galactic binaries, the MREs, etc., more or less sorted, with more or less clean boundaries between all of them. And then some people will need data that is presented in an even prettier and more digested way, which is the L3 data, and which we call the catalog. And then it is really the community or the user's goal to build a story with that data. That is not the goal of the ground segments, that is your goal. So we basically wanted to imagine this level 3 data. And we started writing this document that has been delivered to the project scientists a few days ago. And this is about the story of this document. So just a reminder of the science objectives of LISA, as they are described in the Red Book. So it's a combination of astrophysics, fundamental physics, and cosmology. We look at objects nearby of stellar origin and things very far away of at supermassive black holes. And really, the data products that we produce need to be able to enable the community to reach all of these science objectives. That's really the point of this. So in a more formal way to look at this, so this is taken out of the science management plan. It's the same document that Valeriya was referring to. If you want to read it, it's public, so Google it and you will find it. This is a complex picture, but basically the orange boxes are data levels, and then the other colors are showing the different entities that will produce them. So yellow is everything related to ESA, and then green and blue are both the DDPC, so the Distributed Data Processing Center, and the NSGS, so the NASA Science Ground segments, which will be the European and which are the European and American Data Processing Center. So what happens is that data comes from the spacecrafts. It will be cleaned a little bit, and which will be actually level 0.5, which is not written here. And this data is dominated by the laser phase noise, which actually Ryan just mentioned before. So then this will be processed through TDI, that Oliver mentioned yesterday, and produce level 1 data, which is basically this waveform containing all the sources present in LISA. That will then go through to probably global fits that are meant to find and characterize the different sources and create the level 2. There will be several global fits running at the same time with slightly different features. That creates level 2 data. And then that needs to be consolidated into one unique catalog, and that is the L3 data all the way on the bottom here. The ground segments will also be operating on a much shorter timescale in low latency to produce the alerts that Valeriya mentioned. I'm not going to talk about it, but you should just know that they exist. So this is the big picture of where we operate. In the science management plan, there are a few pointers of what is possible to do with this data, or what it can be. So L2 is really a list of probability distribution functions, of data and their parameters. They have to come with reconstructed waveforms, and they're considered as really analyzed data. And there will be several of them. L3 is a catalog. It is a list of sources with their detection confidence and estimations of their different astrophysical parameters, and the ability to reconstruct H of t, so the strain time series. And L3 is, when I say catalog, you should really consider that it is data and a set of tools to interact with the data, to do preliminary analysis, visualization, cross-match with outside data. And this is what we consider mission end products. It means that the ground segments are not going to deliver anything beyond that. That is really the community's goal to do any science interpretation. The L2 data are being made by DDPC and NSGS, and L3 is done under the supervision of project scientists and science team by the two entities and SOC as well, which is ESA. Okay, so why are we writing this document now, while the first data release is still quite far away? Well, as Nora mentioned yesterday, the mission is currently under its SR, so the System Requirements Review, and the ground segments have to write their requirements. And basically, we need to answer the question, what should the ground segments be capable of doing and delivering? And in that sense, this catalog definitions document is an applicable document because the ground segments need to be able to make data that can go in the catalog. So this was a document about definition. So it's really about what we want, and it's not about how we do it. Of course, if something is completely unfeasible, we have not included it. And so we've already had a bit of feedback with the different ground segments to make a few changes to make sure that this is a realistic document. So ultimately, the people responsible for the data release are the project scientists and the science team, which is why the science team has written this document. So we worked in a working group that was chaired by Nikos and myself with other science team members. From the beginning, we had decided to include outside experts because we really wanted expertise from people who have designed or worked with catalogs and who know what they like and what they don't like and what they really need. For example, people who had experience on other space missions or the ground-based gravitational wave detectors. And then more toward the end, we have called on other experts when we were drafting specific sections, because we really needed to make sure, for example, we had the waveform parameters right. So the expert group, we had a set of telecoms in the beginning to propose the vision of what we wanted. And then when we got into the writing part and the more detailed aspects, the science team took over with some experts, and now it's being reviewed by the ground segments. So what we ended up with in terms of global vision is that we wanted something that we call the golden catalog, which would be the intersection of sources that are confidently found in all the L2 analysis with consistent parameters. Is that there should be a safe list of sources that can be used for non-experts who don't want or don't need to go into specifics of detailed sources. And for example, they want to know what type of galactic binaries is living in this area in the sky. That should be something safe. Go to the golden catalog. Obviously, the catalog should not be hiding anything, and any source that is found with less significance or with less consistency will obviously be available with a different tag. There will be different releases, just like Gaia, DR1, DR2, etc. And a data release is really the data, software, and tools. And each data release is its own, but we had a lot of feedback that being able to trace sources from one data release to another is very important for people. For example, if you want to know what's happening to your favorite galactic binary, or maybe if it has disappeared, but it's something difficult to do. And people should always be using the latest catalog because it has removed the most sources and has the cleanest, should have the cleanest estimation of parameters. We have also realized that we want one unique catalog, not a catalog for galactic binaries and massive black holes, etc. But it's one database, and then sources have certain probabilities to be of a certain type. And of course, a user can query whatever they want, given the masses or the distances they're interested in, and that will naturally give them whatever falls in their bucket. So other things we absolutely need is that the catalog would need to be compatible with whatever standards the astronomical community will be having in terms of data set, of data format. Currently, this is the IVOA, so the International Virtual Observatory Association. And basically it means that if your data follows those standards, it is automatically compatible with all data sets that follow those standards, which is the vast majority of astronomical data sets. And this would naturally enable it to include external information and be added, for example, in something like ESA Sky. Obviously, all metadata to get to the final data products should be available. You know, the methods, the priors, population models, any external data that was used. One of the difficulties with gravitational wave quantities is that they can be time variable, and time itself can be difficult to define an appropriate reference time. In all cases, we will be bound to follow the LISA conventions document. So this is a document that is actually was designed by project and the ground segments together to make sure that we all follow the same conventions and that we don't have problems with 2 pi's, for example. And so this document will follow whatever is written there. One key thing for the catalog is that it will be limited to things assuming 2-body vacuum GR, general relativity. And so anything beyond that is something we consider to be a consortium or community effort. And so the catalog will not include things like triples or the presence of matter or things beyond general relativity. A few other things. So almost all sources, if not all, will obviously have point estimates of their parameters and 90% confidence intervals on these parameters. We will obviously provide as well the posteriors, which can be either as probably a tool that generates posteriors, but it could be static. It doesn't matter. This is not about implementation. And these posteriors can be combined samples of L3 sources, but of course also the individual L2 samples as well. The probability of the source of being of a certain type, which I have already mentioned. We want the signal to noise to be available, and when applicable, the signal to noise as a function of time with the point estimates or as a distribution. We need a detection statistic which translates how confident that we are that this source is real. For all the waveform quantities, when it's applicable, we want, of course, both their quantities in the detector and the source frame. And parameters that are the ones that are being sampled by the global fits will be labeled as such, while more redundant quantities that are just derived quantities are identified differently. And one important piece here is that we want a set of flags that translate how well a waveform fits the data. Some idea of how good is this global fit, because we limit ourselves to 2-body vacuum GR. There will be things that don't quite fit it. And we want a user to know that at least we have an indication that there's something more, which could be a triple for galactic binaries. It could be the presence of gas, for example, for an MRI, or the presence of strong lensing effect. This would be an indication for someone in the community to go look for a bit deeper. We, as the science management plan mandates, we need the ability to reconstruct the waveform, time and/or frequency, and to do this probably at a point estimate or with a distribution. And this should be feasible over a time range that the user can define around the merger, for example, of their supermassive black hole. As we are linking the L3 data to L2 data, we also need to link it to L1 data. in TDI and also single links over time ranges that the user should be able to define. As I've said, all priors that are present in the analysis should be present in the metadata. Things like just flagging sources that are multimodal should be present. And we want a lot of information on the status of the instruments. This is especially relevant for people who also want to search for long signals like stochastic signals. They want to make sure that instrumental effects are not impacting them. In terms of tools, obviously, we want to be able to connect with EM catalogs that follow the same standards, not only in sky position, but also time domain, which is going to be one of the main things in the future of astronomy, and possibly frequency domain, which is actually already being developed for things like SKA. Changes in, for example, units or cosmology models should be feasible. We want a tool that allows variables to be computed over time, with a given, for example, how will the frequency of my source vary over time, including in the future. And this is relevant, for example, for the stellar mass black holes that we could see emerging in the ground-based detectors. Tools to reweigh posteriors under in certain conditions. We want an assessment of the systematics, and then, of course, many tools to visualize the typical corner plots for gravitational wave astronomy, but also anything plotting things over time frequency, etc. Sky maps, plenty of things. There was a lot of work on what type of information we want on instrument conditions and also noise, which is really also includes any stochastic component of the signal. So that includes information on, what is the status of the instrument? Are there any maneuvers being imposed? Is there any any information on, let's say, the temperature, for example? Information on external environmental effects, micrometeorites. Anything that has been identified as, gaps and glitches in the data, we want, of course, to have them as a time series, and they can become binary quality flags for certain sources if that's appropriate. We want models for the noise PSD of all the channels, and then actual estimates of the noise that we want to decompose in instruments, residuals, and then any potential stochastic signals, whether they are cosmological or astrophysical. And for those, we want a measurement or a constraint, meaning an upper limit on any non-Gaussian, non-stationary, or anisotropic effects. So really the type of sources we have been considering are the standard sources that are in the Red Book, galactic binaries, massive black hole binaries, stellar black hole binaries, MREs, stochastics, and unmodeled sources, which is a really tiny piece in the document, of course. And we will explicitly flag the parameters that were searched, but we chose to also be very redundant. For example, you can have total mass and mass ratio versus chirp mass, mass 1, mass 2, etc. And this is because different people want different things. So this is actually the end of my presentation. There is a bit of time for questions. We're quite happy because this is the science team's first document. If you want to just remember a few things, catalog really is data plus tools. It's not just some data that you download. There will be something that we can call the colon catalog, which is the easy, safe to use, but all the other additional data will obviously be available as well. We stick to two-body vacuum GR. So this document will become a public document once the system requirements review is complete, which should be done in about a year. And then the idea is that in a couple of years, it will actually be updated. So this document is not set in stone. And with this, I will stop and see if there's any questions. Thank you.
Thank you very much, Astrid. Questions? Barry McKern is about to ask you a question, Astrid.
Oh, go, Barry.
So can you tell us a little bit more? So using the Lego analogy, let's say there's a pencil in with all the Lego bricks, something that's unmodeled that we haven't expected. What's our sort of agnostic approach to deal with this? unknown, unknown.
So this document is about, how we tell it to the public. It's not about how we find it. But currently there is a category about unmodeled, which is probably your pencil, which has two options. Either it's, whatever non-parametric you have model you have, excess power, you have some spline model, give us that if that's what you found. If your non-parametric model has guided you into using something more complicated, and you have, for the stochastic, for example, you can have all kinds of shapes. If you have chosen a shape, well, give us those parameters and posteriors you have on those parameters. This is what it looks like currently. How you search for it, I have no recommendation.
Question here.
Could you please tell me more about the sorting that's done before the data reaches global fit pipelines?
So, okay, we're talking about Lego. So my view is that the sorting is sort of the global fit. Find the different things and make piles of them, or preliminary lists of them. That's how I was viewing it.
Maybe I could jump in with a question here as well. So you were also talking about the idea of using only the vacuum GR waveforms, but we know that for emeries, even in that circumstance, you can have things like resonant jumps. Is this a matter where there's going to be a gradual development of such waveforms? How is that going to work?
So this was an extended discussion, and because anything that is beyond two-body vacuum GR can be a huge endeavor, and so it is really a choice to not include it as a mandatory thing in the catalog, because it's, in terms of cost for the ground segment, it is simply too much to require that. And so this is why we have this flag that is supposed to catch some of these things. If it turns out that all sources, or almost all sources of a certain type, have a certain flag, because we suspect that all of them have a lot of matter around them, for example, then there is room to include things. But the waveform development is at the interface also between the consortium and the ground segment, because it has the resources that the ground segments can put in it have some limits. And so I think it will depend on how much development can be done there. But we have to stick with that, because otherwise it becomes potentially impossible.
Okay, we have one more question from the room. Are there any questions online? Okay, thanks.
All right, so I have a question that I'm not sure if it's more scientific or bureaucratic, but let's say hypothetically there's a gravitational wave source out there that we are not really expecting, like say stellar mass black hole binaries, right? So if we get surprised, maybe say SMBH triple systems are actually very common in galactic centers, and there's some high SNR thing that is excluded from this catalog that is incredibly relevant for the global fit. How flexible is this setup for something that might be important that is beyond, say, two-body vacuum GR? Can this be adapted, or are we just stuck with a catalog for some years of delay?
No, I hope not. No, we're definitely, this is not, nobody's written this with their blood forever. It's also the idea that this evolves as data analysis progresses, and we realize that we cannot do this. I think, first of all, if a global fit has found something, obviously it has to go in the catalog in one way or another, because we have decided it's a unique database. It doesn't really matter what type it is, in the sense that, as long as it has parameters that can be measured, assuming it's a binary, it has masses and things like this, it can be in there. So I think if it's found in a global fit, we'll simply add it. And it's sort of the same answer as to Korol, is if we find that many of these things do not fit what we had in mind, then we will adapt, of course. It wouldn't make sense to not do it.
All right, let's thank Astrid again.
Thank you.
And Peter, if you wouldn't mind helping set up once more. All right, our final speaker for the first plenary session today is Valeriya Charisi, who's going to tell us about finding black hole binaries of the massive variety before LISA.
Can you hear me? Okay. So it's a great pleasure to be here. It's actually the first LISA Symposium. I made it in person. And of course, like all of you, we are all excited about the different things LISA can detect. But this talk will just focus on one source population, which is the massive black hole binaries, which is actually a source population that is common both to LISA and to pulsar timing arrays. And in particular, LISA will detect the low mass systems that have a mass from 10 to the 4 to 10 to the 7 solar masses, and it can detect them out to redshift 20, whereas pulsar timing arrays are sensitive to the more massive systems with mass more than 10 to the 8, and in terms of resolvable sources, we can detect them in the relatively nearby universe. So whatever I will tell you about the electromagnetic observations and the physics of these systems is common across the mass range here. So I will alternate between calling them massive and supermassive black hole binaries just because the physics is the same. But let's see what these systems are and why they're important. So first of all, when we look at nearby galaxies, like our closest neighbor here, the Andromeda galaxy, we see that every massive galaxy has a supermassive black hole in the center with a mass from less than 1 million to several billions of times the mass of the sun. Here's, for example, a picture of the shadow of the black hole in another nearby galaxy. And we know that this black hole is a very important component of the host galaxy. We also know that galaxies merge very often in the history of the universe. This is how galaxies are built up through mergers of lower mass progenitors. So since every galaxy has a supermassive black hole in the center, the merger will naturally result in a post-merger galaxy that has two massive black holes. And as the merger progresses, the two black holes will get closer and closer together until they become gravitationally bound, and this is what we call a binary. So for this talk, it's important to remember that galaxies also have a lot of gas. In a galaxy merger, that gas will end up at the central regions of the post-merger galaxy, and it can accrete to the black holes and produce bright electromagnetic signatures that allow us to find these systems. And when galaxies merge, we roughly know the basic stages they go in their evolution. So initially, they sink to the common gravitational potential through a process called dynamical friction. This is large-scale interactions with the star and the gas in the post-merger bulge. And this is efficient at bringing the binary to separations of a few parsec. Then the interactions with the intermediate environment become more important. So for example, if we have stars that cross the binary orbit through three-body interaction, the star may be getting a kick, so the binary will have to lose some energy. And of course, you can imagine that the stars are much smaller than the binary, so we need many, many such interactions. And we don't know if we have enough stars there. The other possibility is this gas that I already told you we should expect to have around the binary. So the gas can also remove energy and angular momentum from the system and push the two black holes to smaller separations. And eventually, when they get to small separations, we expect the gravitational waves to be the dominant mechanism that drives the binary evolution until the two black holes merge. So of these systems, the intermediate part has remained the most uncertain. And this was a long-standing problem called the final parsec problem. We now think this is not a problem, first of all, because we see evidence of the gravitational wave background in pulsar timing arrays. So binaries have some way to get to the small separations. But I think the reason we have a lot of uncertainty here is because we don't have observations. We have never seen a binary at a distance less than a parsec. Now, this is also one of the reasons we have a lot of uncertainty in the predictions of the merger rates. And this is one. There are some other reasons, but the predictions of the LISA merger rates have a lot of uncertainty. And this is actually where electromagnetic observations can play a significant role in the next 10 years before LISA flies. So let's see how we can detect these systems using electromagnetic waves. So typically, we observe the initial stages of galaxy mergers and the pairing of their black holes. And over the last couple of decades, we have resolved over 100 systems that have two active massive black holes that are separated by kiloparsecs. And these are called AGN, and they can be resolved across the electromagnetic spectrum. Now, when we go to the parsec scale, resolving these systems becomes more challenging. We can do it only in radio waves using very long baseline interferometry. And this here is the record-holding binary that has a projected separation of 7 parsec. Now, if we go to even smaller separations, even very long baseline interferometry doesn't have the resolution to see these binaries. So we need to infer the presence of the binary from the effect they have on their environment. And one of the promising methods to find binaries is to find quasars, the brightness of which changes periodically. So first of all, why quasars? We think that at least some of the quasars are activated by galaxy mergers. The process of the merger perturbs the gas distribution and triggers the quasar activity. So it makes sense to look at this type of galaxies to find two supermassive black holes. Why periodic variability? Again, I would argue that this is fairly intuitive. We have an orbiting binary that periodically perturbs its environment, but this is also something we see over and over in several simulations. So when we put two orbiting black holes in a gaseous disk, what happens is that the binary initially will act as a propeller, and it will push the gas from the central region outwards, so it creates a cavity of low-density material. But fortunately, this cavity is not completely devoid of gas. We have a lot of dynamical interactions between the binary and the circumbinary disk, so we have these streams of material that come inwards, and we also have these mini disks that form around each black hole and move with the binary. So there are different mechanisms that can produce periodic variability. One is related to these streams that enter the cavity. If we look at the accretion rate onto the black holes, we see that this is periodically modulated. The other possibility is related to these mini disks that form and move with relativistic velocities. So for example, if we have a relatively unequal mass binary, the variability will be dominated by the smaller black hole, because this is the one that moves closer to the edge of the circumbinary disk and pulls the material inwards, and it's also the one that moves faster. So when the secondary is moving towards the observer, it will appear brighter. When it's moving away, it will appear dimmer. That gives rise to periodic variability. The final possibility is when we have an orbit which is roughly aligned with our line of sight. When one mini disk goes behind the other black hole, its emission will be lensed. So we can see prominent self-lensing flares that are repeated every orbit. So The bottom line of this slide is that we do expect bright emission from these systems, and that emission is likely periodically modulated. So over the last 10 years, we had a lot of developments in this field, and the reason was that we had a lot of time domain surveys. So time domain surveys systematically scan the sky and record how the brightness of millions of sources changes over time. And for the first time, we had very big samples of quasars that we could use to systematically search for periodicity. We have done these type of studies across the electromagnetic spectrum, and there are several hundreds of candidates. We wrote a review with DeRosa a couple of years ago, and we compiled the list of the candidates that we are trying to keep up to date. Just to give you an idea of how these binaries look, these are light curves, so practically each plot shows how the brightness or the magnitude or the flux changes as a function of time. And these are some examples of the systematic searches, and these are some examples of candidates that were found individually. I apologize if your favorite candidate didn't make it to this slide. We have a lot of candidates. But what I want to emphasize is that all of them are candidates, because finding periodicity in quasars is extremely challenging. And I will go through the challenges in a bit. So what you need to keep in mind is that a lot of them, and maybe all of them, could be false positives. So why is it challenging? First of all, the periods that we are looking for are relatively long, and in the baselines that we have available, we cannot see many repetitions of the periodicity. That may not be a huge problem for LISA that will probe the shorter end of the periods, but for the entire population, this is a big limitation. So this problem has a relatively easy solution. We can continue monitoring these sources for a long time, or go to archival data and look whether the periodicity is persistent or it's a fluctuation from the noise. And indeed, this has been done in several studies where we looked at archival or follow-up observations, and we managed to exclude many of the candidates. Now, as I said, the complication is that if we have periodicity of a few years, then we need to wait for decades to complete enough cycles. And in terms of the population, we expect many more candidates at the longer periods. The second complication, which is not obvious and not trivial, is the variability of quasars, which is stochastic. So quasars have red noise, and that can imitate the periodicity and lead to false detections. So for example, these are the data points from one of the prominent candidates that were detected in time domain surveys. And the pink on the back is simulation of quasar noise that has just a single supermassive black hole. And you can see that in the limit of a few periods, it's very hard to distinguish the two cases. I want to emphasize that a lot of these searches didn't just forget the red noise. Most of them modeled them with a dumb random walk, which is red noise at the highest frequencies and becomes white noise at the low frequencies. This has been shown that it is a fairly successful description of quasar variability, but it's not the perfect description of quasar variability. So how can we move forward and get more reliable detections? We can improve our understanding of quasar noise. There are studies that go beyond the dumb random walk. We can come up with noise-agnostic methods that assess the periodicity significance without making assumptions of the noise. And of course, getting better quality data will help a lot. Now, the false positive rate is fairly well known in the community, but what we realized more recently is that because of this red noise, we may miss real periodic signals. So, for example, a few years ago with Caitlin Witt, we developed a Bayesian pipeline to select periodicity on top of different types of noise. And we simulated LSST-like data, and we saw how many we can detect and how many we miss. So what I'm showing here is the true positive rate, so signals that are detected, versus the false positive rate, so signals noise that is falsely identified as signals. And you see, when we simulate white noise, we have pretty much a perfect recovery. When we include the red noise, we get to something like 60% of detection rate. This becomes much worse when we use tools like the Lomskargol periodogram, which is one of the very standard tools to detect periodicity in unevenly sampled data, where for LSST-like light curves, we find less than 25% of signals. And it becomes even worse when we look for non-sinusoidal periodicity. So all the previous searches have mostly focused on the simple sinusoidal periodicity. However, from the theory side, we think that binaries produce more complex periodic profiles, so repeated bursts or sawtooths. And when we try to recover non-sinusoidal signals with tools like the Lomskargol periodogram, we fail miserably. We find less than 1% of these signals. So even if they were present in these time domain surveys, we probably didn't find them because we didn't use the correct tools. Now we have started developing some solutions, for example, using Gaussian processes with some flexible kernels. This is showing some promise. We can find about 65% of the signal, roughly at the same level as we did with the periodic signals here, the sinusoidal signals here. Mass filtering has been proposed as a solution, at least to find self-lensing flares. So we are starting to develop some tools to find these signals. And very soon, we will release a very large suite of simulations that has a variety of binary signals with realistic noise and realistic observation quality that we can use to test other algorithms. Now, of course, I talked about time domain observations alone, but binaries produce a variety of signals. So, for example, if there is a radio jet there is a radio jet associated with one or both the black holes, as the binary moves, the base of the jet will move. So we expect to see something like a helical or a wiggled jet. If we have broad emission lines that are associated with one of the black holes, again, they will move with the binary. If we take spectra, we should see coherent Doppler shifts in the spectral lines. If we have very precise astrometric observations, we may see the photocenter moving. So generally speaking, if we take a multi-wavelength view of these candidates, we may be able to uncover independent lines of evidence that can strengthen our confidence in these systems. And indeed, some of these candidates do have additional signatures. The problem is that if you look at each one of these signatures, it's not unique, and it's very easy to confuse it with other things. So for example, in the jets, you may have instabilities or interactions with the ambient matter. In the spectral lines, you may have inflows or features in the disk that produce similar things. And generally speaking, we usually deal with very low quality data. And in that regime, it's very easy to confuse each binary signature with the typical multi-wavelength quasar behavior. Now, I focused a little too much on the challenges, but I'm an optimist, so within every challenge lies opportunity. And the opportunity here is that we will have great time domain surveys coming up soon. And within those, we may be able to discover binaries in the next 10 years before LISA flies. The first amazing time domain survey that we expect is the Legacy Survey of Space and Time, LSST, of the Rubin Observatory. And I have spent my entire career thinking that LSST is the thing of the future. This is actually not true anymore, because the Rubin Observatory is already operating. We had first light a year ago, and hopefully all of you have seen some of the amazing images from the first look data release. In February, they started testing the alert system, and within a few nights, we got over hundreds of thousands of alerts. And now we are in the final stages of engineering tests, and the survey should start within a few weeks. We already have some data in the data previews. The data previews 1 have data that we're taking with the commissioning camera. And we have already collected some data with the LSST camera that will be released very soon. And in a couple of years, we will have the first data release of the survey that will contain a full year of observations. Now, LSST is very exciting for the search of quasar variability for a few reasons. One is that the quality of the data will be much better than previous time domain surveys. LSST will have a baseline of 10 years. It has a semi-regular cadence between 3 to 5 days, and it will alternate between 6 different optical filters. Also, LSST is a very deep survey, so that means a few things. One is that the photometric quality is great. 2, that it will manage to find a very big sample of quasars between 20 to 100 millions. And this is several orders of magnitude bigger than what we have before. And this is very promising because if we want to find the short period binaries, which are more rare in this entire population, we need the very big samples. And these are important for LISA because these are the short period binaries are closer to the progenitors of LISA. So there have been some theoretical studies that predict how many we should find. From this paper, for example, there are predictions that we should find thousands of binaries that have periods between weeks and months. And if we manage to find systems like that, over the course of the 10-year survey, we can collect hundreds of cycles or more, and we can build our confidence that these are indeed periodic sources and binaries. This paper also predicted that we should be able to find LISA verification binaries, so signals that have a period less than a day. So when LISA flies, they should be present in our gravitational wave data. Maybe this prediction is a bit optimistic, but we will see. The other exciting survey that will happen is in the Raman telescope. I don't know if that's very visible here, but this animation shows how the high latitude time domain survey will tile the sky and get time domain observations. So Raman is an infrared telescope, and the launch window is set between August and September this year. So this is happening also. And the data will become publicly available immediately. The time domain survey, I think, is scheduled to happen a couple of years later. And Raman, the advantage of Raman, even though it has a very small field of view, is that it goes deeper than LSST. So that means that Raman will be sensitive to even fainter sources, so it has a chance of finding a bigger population of low mass AGN that are relevant for LISA. And within this time domain survey, we have a chance of finding low mass short period binaries. So of course, with these surveys, we will have massive data sets. And the problem is that our algorithms are not built for that. So typically, the algorithms I showed you, either it's the Lomskargol periodogram that requires millions of simulations, of noise simulations to assess the false alarm probability, or the Bayesian methods, the Gaussian processing methods. They require minutes, and most of them hours per source. And we have several millions of sources, so we cannot scale them to analyze the entire database. So, of course, we started experimenting with machine learning algorithms, which can be very efficient classifiers. So you train them with noise, and you train them with periodic signals, and then you test how they can recover the periodicity or classify the signals. So even the very simple machine learning algorithms, they seem to give us a true positive rate at 70%, which is roughly what we got with the traditional tools. Similar false positive rate of 1%, but we do that in a tiny fraction of the time it would take us to analyze all this data. So within LSST, we are preparing for the first data release. We have a quasar periodicity task force to identify the tools, their strengths and weaknesses, and what is the best strategy for when we will have the data. And we have an ongoing project which is comparing different available algorithms to find what is an efficient algorithm that can be applied to the entire data set and has a high enough true positive rate with a low enough false positive rate. So to sum up, massive binaries can be detected before LISA and can be detected as quasars with periodic variability. We already have a lot of candidates, hundreds of candidates, from analyzing big samples of time domain data. Hopefully I convinced you this is a hard game to play. The periods we are looking are relatively long, so we don't see the periodicity repeating many times in our data. We have red noise, which is a problem both for introducing false detections and for preventing us to find real signals. And of course, none of the signatures that we have considered are unique and easy to distinguish from the typical behavior. But of course, we have a lot of excitement coming our way because we will have great time domain data, both from Rubin and Roman. And we're in the process of developing better algorithms to be able to digest these massive data sets that are coming our way. Thank you.
Thank you, Maria. Questions?
Thanks, Maria, for the nice talk. I was wondering about the last part about finding LISA MBHBs in LSST. So my understanding is that the catalog right now, the mock catalogs are built with simulations which don't have gravitational wave, don't have magnetic fields and other things. And we have excellent talks yesterday where we saw that how the lump features change and other things change, and how gravitational wave can dim some features. Is there plans to include these things also in the future models?
Yeah, so in what we simulated, we used state-of-the-art models, both from analytical models like the Doppler-boosted self-lensing, but also from hydrodynamical simulations. You're right that we are missing a lot of physics in these simulations, but yes, as our understanding of the models becomes better, it's relatively easy then to take the predictions of the simulation and make mock light curves that look like what LSST will detect.
But do you think we will miss things if we don't include this physics?
Yes, if we use them as templates, it's very likely if you don't have the correct templates that you will miss what you don't know what you're looking for. One hope is that with machine learning, maybe they can become a bit smarter and interpolate between what you have trained them on, but we will see.
Savik.
Thanks for a great talk. And I guess I'm wondering to what extent you think that that progress on understanding AGN variability can also assist, for example, in eliminating false positives. So obviously, if we understand what the true binary periodic signal looks like, that helps us. But if we can understand what are producing many periodic looking things, obviously red noise, overmodeled red noise is one thing, but there are some things that look kind of periodic that are really maybe not binaries. Do you have any?
Yeah, so I totally agree with what you're saying. So understanding the underlying noise, it's always useful for finding signals. For a lot of people, this is their main signal. So there's a lot of work in understanding quasar variability, and the dumb random walk model was sufficient for the quality of the data we had from optical ground-based time domain surveys. If you look, for example, at light curves from Kepler, we already know that this model is not good enough. So hopefully with LSST and having a huge sample of quasars, we can also quantify the variability much better. And one other thing I can say is like one model that goes beyond the dumb random walk is the dumb harmonic oscillator that has a quasi-periodic feature built into that. So hopefully that will help us remove a lot of the false positives.
Thanks.
Thanks, Maria. Great talk. So one comment and then a question. So at redshift less than 1, the electromagnetic follow-up of merging massive black hole binaries, we should have a relatively good chance of localizing the galaxy host, whether or not there is an AGN. So we should be able to just find the emission from the host galaxy. However, AGN emission will be pretty crucial if we want to localize the source on the sky at redshifts higher than 1, where there will be many galaxies in the LISA localization volume. Given that these binaries will be at high redshift and with mass likely less than million solar masses, which of all the signals that you told us about would you prioritize in searching them? And which of the methods for modeling and classifying the light curves do you think need the most urgent development, basically, so that we can get there and find those quasi-periodic variable
Yeah,
sources?
so if you're saying
Thanks.
methods within the quasar periodicity or methods within general signatures?
We'll start with the quasi-periodicity if that's easier, but feel free to comment on all methods in general.
I would say, I would start with the periodicity because this is what I know best, and also this is what we will have a lot of data to search through. I would say we know, at least from the theory models, that simple sinusoids are not what we expect most of the time. We expect them when we have circular orbits with relativistic Doppler boost, but in most cases, we will get more complex periodic profiles, which so far we would fail to detect. So I think going forward, we need to start thinking how we can be more efficient at detecting these systems. I would also say that even those that get to 60 or 70% is not a good enough true positive rate, because you're looking for something that is very rare, and it's very easy to miss, especially if the signals are weak. So how we can build algorithms that go to higher true positive rate. And I would argue that I'm willing to tolerate a high false positive rate if we can get a true positive rate that is also high, because with long-term observations, we can filter out the false positives. So my hope is that we can get detection rates that are much higher than the 70% we can do now.
All right, let's thank Maria and all the speakers again. Do you have a question online? Oh, sorry.
So the question online is, once you have identified a strong candidate, how can you confirm it? How can you be sure that it is a real binary black hole and not something related to disks and jets?
That's a very hard question. The answer is I don't really know. Having a lot of cycles helps. Having additional signatures also can help. Finding gravitational waves would be the definitive answer. Maybe we're a bit far from that. But also in the electromagnetic data, you may find the chirping behavior. That may not be very common in this data quality to detect it, but there you could find the gravitational wave evolution in the periodic signal.
Okay, I think we have at least one announcement related to the group photo.
All right, we were going to do the group photo now, but it is raining outside, so our plan is to delay it till tomorrow's morning break. It means tomorrow we want to be, on time. We want to start promptly at 8:30. We're starting at 8:30 tomorrow, right? And so, and get through and have time for the photo and then the coffee break and keep on schedule after that. So let's plan for that tomorrow. Some other news, McKeldin Library is open today and available for poster printing. So I know at least a few people were hoping to print a poster. That is still possible today. You go over there and it's on the second floor, I think, and it's self-serve and $5 per square foot. So they'll help you do it, but you're basically printing it yourself. We will have a coffee break now. We'll come back. Since we aren't doing the photo now, let's plan to be back here at 11 instead of 11:10. So we'll give you a full half hour for that. Another note is that tonight is the public lecture. We encourage you to all come. Please come if that fits your schedule. One note that, if you're thinking about food before the lecture, normally the food shops are pretty much shut down. Only Chick-fil-A stays open that late in the Stampede. However, for us, the Subway is also staying open this evening. So you'll have those options for eating in the food court area here if you stay in the building here up until the public lecture. With that, I think we are now going, question. Oh, right, good point. No food or drink in the theater. You have to eat it before you go in, but the food court has plenty of seating outside. Just be sure to finish it up before coming in. Thanks. Great. Anything else? Okay, so coffee break. See you in half an hour at 11 o'clock.